Okay, so last month we looked at Boost.Asio and asynchronous IO library. We looked at how to get started with that, how Boost.Asio introduces what's called inversion of control, and everything is set up as an asynchronous operation with a work queue, and the items get processed through the work queue in the order that they were submitted to the work queue. And this allows you to monitor different input sources and wake up when there's something to do. And we looked at how to combine a timer and input from the keyboard and input from the serial port. And we would wake up whenever the timer fired, whenever there was data on the serial port, or whenever you had typed something on the console. And this month, we're going to look at, let's go over here. We're going to look at how to do TCP IP networking. And if you've done any TCP IP networking before, there's some things you have to do before you can actually start communicating with some host on the internet. First, you usually don't start out with the host's IP address, its unique address, either an IPv4, which is 4 8-bit values representing an address, or an IPv6 address, which I believe is 4 16-bit values to identify a machine on the internet. IPv6 mostly just extends the address space of IPv4, but most of the time you don't care because you're not dealing with addresses, you're dealing with host names. So the first thing you have to do with a host name is to resolve it into an IP address so you can open a connection to a service on that machine that's identified by the address. This is done through the domain name system. And normally you don't care, unless you're an administrator, you don't care about the details of the domain name system. You just need to get an IP address for a host name. So look to see how we do that. And then the example we're going to use here is Network News Transport Protocol. Now, most people don't use NNTP or usenet much anymore. It seems that all the discussions now have moved over to things like discourse or a web forum or some kind of thing like that. And we can debate the pros and cons of that situation, but that is the situation. And as a consequence, there's no real C++ library for NNTP. There's not even a good C library for NNTP. So it's kind of useful to look at this protocol just from the point of view of how do we implement basic support for this protocol in C++ using ASIO. And NNTP, like other protocols of its era, namely SMTP, which is Simple Mail Transport Protocol, and FTP, File Transport Transfer Protocol, these are so-called conversational protocols. So you establish connection with a server, and then you're sending commands and receiving responses from the server that you're connected to. Now, NNTP is for reading articles. Articles are grouped into news groups, and then news groups are housed on some server. Now, originally, the articles were just in a directory on the machine and not obtained over the network. But then, when NNTP was introduced, it became feasible to have the idea of, well, maybe I want to get articles from multiple servers and not just from one place, my local machine. Maybe I want to talk to multiple servers out on the internet and get articles from more than one place. And there's also the question of, because this is a long-lived conversation between a client and server, how do you handle things like timeouts? If most servers will drop a client connection if you don't issue a command or anything like that, after a certain amount of time. So this is how do you handle when the server drops your connection, or maybe the server goes down for maintenance while you're using it, so it may disappear out from underneath you. So how do you handle network errors? And there's the question of how do you keep this inverted control that's managed by Boost.Asio, how do you keep that alive? Because in our previous example, we always had a timer that was, every time the timer fired, it always queued up another timer event so that it would keep going forever. And the way that we exited the program is that you typed some input at the console, and then that would cancel any of the pending I/O operations that were keeping the main loop alive. So the main loop is not, in this inversion of control scenario, the main loop is not written by you. It's inside the Boost.Asio library. So if you're sending having a conversational protocol where you're sending command out and getting a response back, well, once the response comes back, then there's no more pending I/O operation. So there's the question of how do you keep that Boost.Asio mechanism alive, keep that main loop running. You could certainly queue up timers and keep firing a timer as one way to do it. There's another way to do it, which we will take a look at. And there's an interesting wrinkle here with TCP/IP. Unlike a serial port, with a network connection going out over the raw internet, you may want to secure that connection from eavesdropping by using transport layer security, TLS. Now, in the NNTP protocol, there's a command that will let you switch the conversation between the client and the server from a plain socket to a secure socket. And we'll take a look at that. There's also the option of connecting directly to a news server on a different port, where that port is reserved specifically for TLS-oriented connections, so-called open SSL style connections. I mean, SSL is the old name, secure socket layer. Transport layer security is the newer name. It's the same idea. It's just an evolution of the standard. So technically speaking, it's TLS, not SSL. But if you hear people say SSL, just recognize they're not actually referring to the secure socket layer specification from, say, the year 2000. They're talking about transport layer security. So let's take a look at some code here. So I'm using, this is my VC package manifest. I'm using VC package to obtain Boost. Now, Boost.Asio depends on many other Boost libraries, and I just found it always easy now to consume Boost through VC package, because VC package understands the chain of dependencies between any library you want to consume and all of the libraries that it depends on out of Boost, and it will go and obtain all the dependencies. It will build any built dependencies that are needed. There's a few libraries in Boost out of the many that are in Boost that need compilation, and if that's the case, then VC package will build that for you. And VC package has the concept of optional features that go with the library, and the feature is called SSL, but as I say, it's really transport layer security. That is an optional feature of Boost.Asio, and I've declared that here in the little features array. I'm using gtest for some unit test stuff, and I'm using curses calls, which I hacked this example up on Windows, so I'm using the PD curses library, which is a Windows only curses library. And in my main CMake, I am doing a find package to get Boost.Asio as a imported library target. Now, there's no imported library target created for header-only libraries when you do a find package boost. So in CMake, find package is how you locate installed libraries. VC package took care of downloading, building, and installing the library in my build directory, my CMake build directory, so that find package will succeed. And there's a way to specify which particular component out of Boost you might be looking for, but header-only libraries aren't listed as a component. And because ASIO is a header-only library, what I do is just look for Boost, and if we found Boost, then I'm going to go ahead and make so-called interface libraries that give me a way to specify that I just want to depend on Boost ASIO, and I don't need to worry about, for each of the things that depend on Boost ASIO, I don't need to worry about these Boost include-ders or various compile definitions. I'll just briefly explain what this is. On Windows, when you include Windows headers, if you don't specify the value of this Win32 WinNT preprocessor definition, if you don't specify that, it'll default to a reasonable value, but it emits noisy warnings in the build, and I don't like seeing warnings in my build, so I took care of that to say, what version of Windows I'm going to target so that it's not targeting a default version, but it's targeting a specific version, and then that gets rid of the warning. Now, because I'm also using Open SSL, because I'm going to use the SSL feature supported by Boost.Asio, I need to go and identify those libraries for setting the include path correctly and setting the library dependencies. And so just doing a standard CMake find library to find the libraries and a find path to locate a header file that comes in the OpenSSL distribution. I identified those names by just looking in the build directory after VC package had built and installed these libraries. And so I am creating an import library for the crypto library, which is handling all the cryptography stuff. That's the majority of the built code in OpenSSL. And then I'm creating an imported library for OpenSSL itself. And I'm saying that OpenSSL depends on crypto, which it does. And then in my code, if we go over here, here's the make list for my little application. In my code, I just say that I'm depending on OpenSSL. My little NNTP library here is actually just kind of, I'll be honest, it's a little janky. I just ended up in this code we're going to look at, I just ended up directly using Boost.Asio. I didn't fully pull out everything into a library for this example, but the NNTP library depends on, if you look at its CMake, it in turn depended on Boost.Asio. So I guess technically speaking, since I'm not really using that library, I should just have Boost.Asio here. And if we build, everything should just be fine. It's just going to change. It's going to rebuild my source file because I changed the library dependency structure, but everything still builds okay. So let's just get in here and start take a look at this code. So in standard Boost fashion, there'll be a single header file that you can include that will bring in. I think technically speaking, I don't need these other header files if I include this Boost.Asio. The stuff in ASIO is pretty deeply nested in namespaces, so I just find it handy within my own code to shorten them up a little bit. So just ASIO is namespace alias for Boost.Asio, and then IP is a namespace alias for Boost.Asio IP. So they tend to have things pretty well segregated within ASIO so that there's not everything is just dumped into one namespace. Things are segregated around so that TCP/IP stuff is in a TCP namespace within IP, and so on. So let's start down here at the main. So probably let's do this. Let's run this program to show you what it looks like. Set a startup project. Might need to bring this over here. So the screen is split into 4 areas. This is the chatter, the conversation between the client and the server that it's talking to 4 servers simultaneously. I say simultaneously, but it's really they're just getting queued into the Boost.Asio IO context. As we discussed last month, the IO context is the thing that does everything. And inside here in this chatter, if it says bracket S bracket, that means that that's part of the chatter that happened over a secure TLS connection. So if we run it again, let's run it again now that I got the... Oh, let me pause it. So you can see here, we've got little notifications coming from my program that we are connecting, and then it's connected, and then here's the greeting from the remote server, and then I'm sending this command, and then here's the beginning of the response to the command that includes this little 3-digit status code. This is very similar to FTP and SMTP if you've ever looked at those protocols. Some remnants of this are also in HTTP. It's just that HTTP is not as conversational. So there's not like in HTTP there's like a single command and then you get back the payload response. It'll have that 3-digit kind of code in there to indicate the overall status of the command, and then there's arbitrary text that can come after that status code. And so you see here, all these servers, they're all getting the same sequence of commands. Here, let me do this. Let me make this window bigger and change the properties. Let's make it 60 lines high. Okay, and let's see if I'm lucky. And now I run this again. Oh, it didn't remember my size. Maybe I need to do it this way. If I get this to be bigger, you can see more of the chatter from the 4 servers. There we go. Okay. So let's pause it. So the first thing we have to do is resolve a host name into an IP address, and then we have to connect. We have to initiate connection to that remote server, and then we get a notification that the connection has succeeded. And in NNTP, when you connect to a server, the very first thing the server does to send you a greeting message that contains this 3-digit status code and some arbitrary text that's coming from the server. Usually it's just text that identifies what new software the server is running. You can see 3 of these servers are running the software called INN 263, and this one down here is running INN 280. So it's got a slightly newer version of INN. And then I'm sending a command to the server, this capabilities command, and it responds with status code and some text. Most of the time, the text that comes after the status code is just kind of informational for debugging purposes. Sometimes, according to depending on the command and the protocol, sometimes that text will contain additional information that you can parse out of it. And then here's the beginning of the response. Now you can see I have 2 lines of response in this capability list from this server. I have 1 line down here. I have no lines yet down here and no lines yet down here. If we continue, you get more lines of output, and these, let's stop it again, pause it again, that you get more lines of output, and you see one of the things that came back in the capabilities list was that the server supported transport layer security with by indicating it has this start TLS capability. And so I sent the start TLS command, and then the response to that command was start negotiating the TLS connection. And then once I've switched to the secure connection, I'm outputting these little status strings with a little bracket, S bracket, to indicate that we've switched over to a secure connection. And then I issue the capabilities command again over the secure connection, and then the server is, according to the specification for NNTP, the server may adjust this set of capabilities that it provides over a secure connection. Like, for instance, maybe it doesn't allow posting over a non-encrypted connection, but it does allow posting of articles through the encrypted connection. Most definitely, one thing is that it should not advertise the start TLS capability once you've already switched to encrypted communication. So if we continue again, so here I'm just getting the result of the capabilities command again once we've connected in a secure fashion, and then I'm sending a quit command over the secure connection, and then it responds with the appropriate response to the quit command that, we're terminating the connection. And then I'm just sitting here in curses waiting for a character to be typed to quit the program. So if we go back here over to the source code, that's what this program looks like when we run it. And what's happening in terms of ASIO, this little curses thing, this is just a little RAII style wrapper I wrote to initialize curses and shut down curses, so that no matter how I exit out of here, curses will be appropriately shut down when I exit. My little reader class here, this is just something to initialize my SSL context. I have told it that I'm going to use TLS version 1.2. I was using version 1.3, but one of the NNTP servers that I was negotiating with here didn't support 1.3, so I dropped it down to version 1.2. I'm using the same SSL context for all the connections. You could have an SSL context per connection to allow different connections to use different versions of transport layer security, and you could recognize that when you tried to negotiate the version 1.3 of the TLS specification, if that failed, you could drop down to a 1.2. That would be the most the secure way to use a TLS connection when you're talking to servers that you don't control, right? Start with the most recent version of the specification and then fall back to older versions, because the more recent versions are there to correct perceived or real deficiencies in the previous versions. So you want to use the most recent version that you can support on both client and the server. Now, if you've done any kind of cryptography stuff before, of which TLS uses cryptography to secure the connection, now we should clarify what we're getting here. We are not getting authentication. Authentication is the means by which a client and server can validate that the identity of the thing on the other end. We're not proving who we are. We're just simply using a secure connection to prevent data the exchanged between the client and the server from being eavesdropped on random hosts on the internet so they can't see in the clear what data we are sending and receiving between the client and the server. That's what we are getting by using TLS. So it is encryption that prevents eavesdropping, but it does not secure the identity of the client or the server. I can't be certain that the server I am actually connected to is the one that I think it is, like somebody hijacks the domain naming system, steals your DNS entry for your server name, and then I got the IP address of a bad actor instead of the real machine when I requested that the host name be resolved into an IP address. TLS does not protect against that. And once I'm connected, the server has no way, just via TLS alone, to identify that the client is who they say they are. So, for instance, when I post articles to Usenet, is the article actually coming from who it says it's coming from, or is it forged? TLS does not address that problem. There is an authentication mechanism in the NNTP protocol, and most servers these days are not so-called open servers that allow anybody to post. In the capabilities that are returned, the post capability indicates that the server supports posting, but that doesn't mean that anybody can post. If you post, you may get a response that says you have to authenticate before you can post. Most servers these days, because people on the internet now are jerks, you can't really trust the internet as it was in the case of, say, like 1990. You have to authenticate yourself to a server, and generally these days a server only allows you to authenticate to it once you are a paid client. In my case, I use a server provided by Xmission, local ISP, and they let me post to that because I've authenticated myself to their server, and so they allow posting by their customers. I'm their customer, so they allow me to post messages through their server. However, generally speaking, you don't have to be authenticated to read articles. There's plenty of servers that allow you to read articles without being authenticated. They may require you to be authenticated to read certain groups within their server. But again, authentication is a separate issue from just encrypting the connection to make sure it's secure against eavesdropping, which is what we're doing here. Now, the interesting part of this example is not so much that it uses transport layer security. There are plenty of examples in the Boost.Asio tutorials and examples that show how to do SSL communication with a server. However, what they typically do in the case of, say, obtaining a response from a web server over HTTPS, that's HTTP over transport layer security. HTTPS, the way it works is it uses a separate port. So there's the standard port 80 is for HTTP in the clear, and then there's a different port. I don't remember what number it is off the top of my head, but there's a standard reserved port for HTTP over transport layer security, in which case, in the chat, it's port 443, Ed says. I believe that's right. That sounds right from memory. That special port is reserved for communicating with a web server over TLS, and that means that as soon as the connection is established to the server, you must initiate the TLS handshake that bootstraps the socket from plain text to encrypted text. Now, in NNTP, while there are servers that support so-called NNTPS, namely, once again, it's similar to HTTPS, that once you connect to the server, you must immediately initiate the TLS handshake to bootstrap the socket from plain text into encrypted text communication, in older NNTP implementations, what you do is you send a command that says, you get the capabilities from the server. The server says, I have the start TLS capability. That means it supports the start TLS command, and you send the start TLS command, and then you negotiate the handshake to Bootstrap encrypted communications. So there's an initial plain text exchange, and then you switch from plain text to encrypted text. Now, this is similar to a facility in SMTP, because SMTP, Simple Mail Transfer Protocol, did not originally support encryption because it's one of the oldest protocols that's still in use on the internet. So all this encryption business wasn't even a thing when SMTP was created initially. So SMTP also had a way to bootstrap your way into an encrypted conversation from a plain text conversation. And I couldn't find any example of doing that switch in the middle for Boost.Asio. I found plenty of examples where they bootstrapped their way into an encrypted conversation like immediately upon connecting, but we're going to look and see how you do it in the middle. And this may be useful if you have legacy protocols in your company and you would like to upgrade them to encrypted communication, but you can't necessarily negotiate that all the firewalls open a new port. Because if you're going to do HTTP and HTTPS, that requires one port for the clear text communication, port 80, and another port for the secure communication, port 443. Well, if you've ever worked in IT or worked on an application where you're trying to get IT to open holes in their firewall in order to let your application communicate through, it's nearly impossible at this point. Anybody at a reasonable organization is going to refuse your request to open up new ports, and they're probably not even happy about opening that port for your legacy communication that you have. This is why a lot of applications have switched to using HTTP and HTTPS as the transport for their remote procedure call style stuff, which we'll look at in a subsequent presentation next month. But in the case of NNTP, I've coded up inside this little example code how to upgrade the connection to TLS in the middle. So as we saw here in our main, we're instantiating this reader class. The reader doesn't really do much. It just does some initial setup of the SSL context that we're going to share for all these connections. And it knows how to resolve host names into IP addresses. And once it has IP addresses, these resolver results, it's going to instantiate a connection to handle the conversation. So all the interesting part with the network protocol of NNTP is going to happen in this connection class. So if we look back here at the main code, we've got this list of news servers. We're going to add them into the reader, and then we're going to set up a little command window here just for curses, just so we have something that we can wait for after the reader has finished. And I'm going to call this reader.run, which is really going to do all the work, and that's really just calling run on, if we go back up here, the IO context from Boost.Asio. It keeps popping up and making it hard for me to highlight. There we go. The IO context from Boost.Asio, which is the thing that does the inversion of control. It's what we talked about last month. And so what's new that's going on here compared to what we discussed we're talking with serial ports and timers is we've got this SSL context. We're using the TCP IP resolver. The resolver is the thing that interacts with the domain name system and resolves host names into IP addresses. And fortunately, the mechanism of resolving a host name into an IP address, it's using the domain name system protocol underneath the covers, but really that's all encapsulated by any kind of Berkeley socket style library when you call these C-style functions that resolve host names into IP addresses. And really, what's being encapsulated here in Boost.Asio is it's just encapsulating the differences between resolving host names on Berkeley style sockets, BSD socket library versus Windows sockets. So it's just taking care of those platform differences, whatever they might be, and providing them to you in a consistent manner. Now, when we add a server, doing a little bit of curses junk, and then the interesting part is we're going to ask the resolver to resolve a host name asynchronously. So we pass it in the host name. We pass it in a string representation of the port we wish to use when talking to that server. If you've done raw socket programming, I believe the raw socket API call is called get service by name. That resolves a service from a name to the standard registered port number to use for that service. If we were talking to a NNTP server over some custom port, then we would use a port number here instead of the service name. And the way all of the stuff in ASIO works is this just initiates the asynchronous operation. It basically queues a work item onto the IO context for it to run, and it's out of its work queue. And when the result comes back, it will invoke the callback with a particular signature, and all the Boost.Asio functions that initiate asynchronous operations, they document what the expected signature of the callback is to be. There's always an error code that's passed in first. And just to save typing, I made a little type alias. The error code is always of type boost system error code in the Boost.Asio flavor of ASIO. And just to save myself from typing that over and over again, I just made a type alias for that. And it's going to give us back a set of results. And again, I just made a type alias to save myself a little bit of typing. And you might ask yourself, why is that plural? And the answer is that a single host, although it has a unique name, it may have more than one IP address. And you may ask yourself, how can that be? I thought IP addresses identified a unique machine. And they do, but they are more specific than that. So they identify a unique network interface on a machine. So I can plug I can plug multiple network interface cards into a single machine. That machine has a single name, but it may have multiple interfaces by which it can be addressed, and each of those interfaces has a distinct IP address. So what comes back from the resolver is not necessarily a single address, but multiple addresses. And what we do is we run through all of the addresses that came back, and we take the first one that successfully connects. So we initiate this resolve operation, and then we're going to go into our resolve callback. And the first thing we're always going to do in these callbacks is check the error code. And in my case, all I'm going to do is print out, some kind of error message through curses, and then just return immediately from the callback. So what happens when we get an error? So this asynchronous operation initiates. It queues a work item on the IO context. The IO context takes the next available work item and processes it. It gets the result of the asynchronous operation and hands it off to the callback. If the callback sees that an error occurred and it returns without initiating any further asynchronous operations, then a work item was removed from the asynchronous work item queue, but no more items were added, and the IO context will exit its run method as soon as there are no more work items on the queue. And the way I've got everything set up here, basically, if one of the servers errors out, but the other servers don't, then the server that errored out will get a little error message in its portion of the console window that I've allocated through curses, and it will stop the conversation with that server. The other servers will continue processing asynchronously until their conversation is finished, in which case they're not queuing any more work items on the asynchronous work queue, and then the work queue exits down here, and then the program exits, waiting for me to type a character before quitting. Now, so in all of the cases where I do error handling, that's my solution to error handling, is I just stop the conversation at the point where the error occurred after having printed to the console some kind of error message, so I know what happened. Me, the user. But if we succeed, what we're going to do, so we succeeded in resolving the host name to a set of resolver results, and then we're going to try and establish a connection to the one of the IP addresses that came back in the result set. And so in the constructor for my connection object here, I'm taking the resolver results, and what I'm trying to do is to do a connect on the results. Now, it's so common in TCP/IP communication for you to accept the first successful connection to one of the IP addresses given in this resolver result set, that they've got an overload to async connect in Boost.Asio that takes the socket and the result set, and it will iterate through the result set and invoke the callback for the first one that succeeds, or with an error code if none of them succeeded. So once we get into this handle connect callback, now we're connected to a specific endpoint on that server that was listed in the result set, and the specific endpoint that we were connected to is given to us as a parameter in the callback to that's invoked by async connect when the connect succeeds. Now, to the careful observer here might have noticed this little M-socket lowest layer business, and we kind of skipped over the members that were being initialized here, so let's go take a look at them. So I just have a string. That's the name of my server. I have a curses window. That's the place where all the chatter from this particular server is going to go. I have a, you might not be able to tell, but this is cap S socket. That is my own type def for a Boost.Asio SSL stream, and the stream is parameterized on a TCP IP socket from Boost.Asio. So transport layer security specifies how a stream of bytes are, it specifies how the encrypted communication is negotiated between the client and the server. This involves the exchanging of some keys, because the whole point of an encrypted conversation is I have to be able to decrypt on both ends in order to understand what was actually transmitted in and received in the conversation. So there's a way that the client and the server do this handshake, and they exchange some keys, and then each side knows the public key that's used to decrypt the data that's encoded with the private key that's used by either side. And TLS has, lots of details on how this is accomplished in such a manner that it's difficult for somebody to snoop on the negotiated handshake and be able to decrypt the stream without being the person that initiated the connection. It's just one of those, tricky things in cryptography where a bunch of smart people figure out how to do these sorts of things in ways that's not, it's not impervious to attack, but it's not susceptible to casual attack. I don't want to overstate the strength of it, but I don't want to understate the strength of it either. And basically, this is the fundamental underpinning of why people feel safe doing online banking, right? You don't want to do online banking over an unencrypted connection, because then people could just snoop the connection and see what you're doing. Your account number and how much money's in your account, all that stuff. You don't want that happening. You want secure communications in order to be able to do financial transactions over the internet. So that's my socket class. And, why did I make this type alias? Well, I just did it because I'm using Clang format to line up my declarations here, and I didn't like this ridiculously long declaration for my little socket variable. That's all. There's nothing magical about the type def. Now, when we read and write data over a socket, we have to have some place to put it, and it's convenient to use this StreamBuff class from Boost.Asio as a place to store and retrieve the data that we're reading and writing. This stuff down here, the command string and this boolean about returns a data block, a little status enum, and the expected status, those are all just, and this data block vector of strings, those are all just implementation details of my little mechanism that implements the NNTP command response chatter for the protocol. This little boolean saying using TLS is how it is the thing I'm going to switch from false to true once I've negotiated the transport layer security connection as I bootstrap the conversation. So the important thing down here is there's this socket. It's a SSL Boost.Asio SSL stream parameterized on Boost.Asio IP TCP socket. Now, the way transport layer security works is the TLS specification doesn't actually say anything about the communication mechanism used to talk between client and server. It just specifies how the encryption works. So that's why an SSL stream is parameterized by TCP IP socket. There's nothing that says you can't have a TLS encrypted conversation over a serial port. It's not a whole lot of benefit in doing that, because a serial port is generally a point-to-point communication between two devices that are physically close to each other, and it doesn't go out over a public network typically, so securing the chatter across a serial port connection doesn't usually make much sense. Maybe it makes sense if that serial port is actually connected to a modem and the modem goes out over the public phone network. People can and have snooped public phone network circuits. So maybe it makes sense to have TLS over a serial port chatter in that case. Realistically, what people do in that situation is not so much TLS over the byte stream sent over the serial port, but they use the serial port to bootstrap a TCP/IP protocol suite over the serial port, like point-to-point protocol or a serial line interface protocol, and then they use SSH and TLS on top of that internet protocol that's bootstrapped over the serial port. But nonetheless, TLS just specifies how the encryption works. It doesn't say anything about what the transport mechanism is, although most often it is a socket. So that's why this SSL stream guy is parameterized on a type. In this case, it's the TCP IP socket type. And because of that, when we do the connect, we haven't yet established the secure communication through TLS yet, because we're not connecting over a special port reserved for TLS when talking to an NNTP server. We're talking over the plain text port, and we're going to bootstrap the TLS conversation later. So what you do until you've established the secure communication, you need to use not the SSL socket. I mean, I've called this variable socket here, but it's really, it's this SSL stream, right? It has this IP TCP socket inside it. And by calling this lowest layer function, that's how I get at that encapsulated, unencrypted socket that sits underneath. And that's what I need to use for my connect. There was a lot of explanation there, but it's just kind of it's the main difference between this example that I'm showing about how to bootstrap TLS in the middle versus the examples you always see where they just assume TLS from the outgo. If you assume TLS from the outgo, they do the connect and then they immediately do the handshake. So we're going to do the connect. And if we didn't get an error, I'm not going to really discuss error handling anymore since it's all the same for all these guys. We're going to put out in our little chatter conversation window, our curses window for this server connection, I guess we should say, that we've connected, because this is the response to the async connect. This is the callback that's invoked. We've connected on this particular endpoint. In my case, I didn't dump out the endpoint. I didn't particularly care. And in NNTP, the first thing that happens when you connect is the server sends this greeting line. So we need to receive a line from the server, and having received a line, we need to handle whatever was in that greeting. Let's just take a look briefly at receive line. So we're going to invoke this async read until, which is a handy facility in Boost.Asio. It's particularly handy for this NNTP protocol because everything is delimited by lines as opposed to a raw binary protocol where you might have to read a count and then you know how many bytes are in the response or in the command based on the byte count that precedes the payload. When we looked at cap and proto for serialization, that's how cap and proto encodes things. Everything's encoded with a count of bytes first and then a payload that's that many bytes after. But NNTP is a text-oriented protocol, so all the commands are delineated by a carriage return line feed pair. And just mention here, when reading these internet protocols like HTTP, SMTP, FTP, NNTP, be careful that you terminate your commands and you parse the responses accounting for the carriage return line feed pair that almost always terminates these lines. It's not just a new line, and it's not just a carriage return. It's specifically a carriage return new line pair. So async read until takes a socket and the place where the read data will go, and it's going to read data up to and including this termination string. And then when that operation completes, namely it's read everything up to and including the termination string, then it will invoke the handler. Now, if you look at the other async read methods in Boost.Asio, or if you're familiar with network programming, you may know that just because you requested to read a certain number of bytes, it doesn't mean that that's the same number of bytes that the underlying I/O call from the operating system returned to you. So you may request, I need to read 60 bytes, and it may say, I couldn't get you 60, here's 10. Ask me for the rest later. And in Boost.Asio, there's a similar function to async read until called async read sum, and it will read whatever bytes are available and tell you how many are available. The question in the chat is the carriage return line feed server platform specific or the spec? It's the spec. So doesn't matter whether you're communicating from a Windows machine or a Unix machine, you must send carriage return line feed to terminate the commands that you send, and all the responses will come back with carriage return line feed terminating each line of the response. And if you look at the raw byte dump of an HTTP request, with Wireshark or some other kind of, thing monitoring like that, or if you ever look at the implementation of an HTTP library, you will see that carriage return line feed sequence specifically placed in there. And you can always tell when somebody implemented it wrong because the response will come back and it only has a line feed, or it only has carriage return and it doesn't have carriage return line feed. So for a lot of these things, the advice is be conservative in what you generate and be liberal in what you accept. I'm being strict in what I'm sending and accepting. That I'm always looking for a carriage return line feed. I'm not looking for, to handle bogus implementations of the server that don't do it right. The reason I'm not so worried about that is because, as we saw in the dump on the terminal window, pretty much everybody uses INN to implement their web server these days. So really, there's not as much variation in implementation as there used to be when NNTP was more popular. Pretty much everybody runs INN these days. And INN has been around for years and adheres strictly to the specification. So I'm being a little, lax in what I'm willing to accept. I'm being very strict. But, so async read until is what we're using to make sure that we don't invoke our callback until we've gotten a full line worth of data. Now, you notice here that I'm calling async read until on the SSL stream if I've gotten to the point where TLS has been bootstrapped. If we haven't yet gotten to the secure communication, then I'm calling this next layer function to get at the underlying socket to pass to async read until. And you might ask, well, why did I use next layer here compared to lowest layer when I did the connect? And the answer is I think that next layer up here on the connect would have worked just as fine. But when I used lowest layer in these line-oriented calls, I got a compilation error. And that's because the type of the lowest layer is not necessarily the same as the next layer. It's kind of like, Russian nesting dolls of types. And the functionality supported by async read until required the type of socket that's in the next layer down, but it wasn't supported for the type of socket that was at the bottom layer. So I had to use next layer instead of lowest layer here for this async read until call to compile properly. But and for the purposes of what I'm implementing, it's not, obviously there's technical differences because they're different types, lowest layer versus next layer, but every socket, even the lowest layer socket representation, supports connection. But not every socket supports read until, and I believe the difference is that if you know anything about network protocols, you know that actually transmission control protocol, which is TCP, this is the protocol that specifies reliable connections between two endpoints. Reliable meaning the bytes are delivered, are guaranteed delivery, and are guaranteed to be delivered in the order in which they were sent. Now, TCP itself is a protocol built on top of the lower level protocol, namely Internet Protocol. An Internet Protocol makes no guarantee or makes no promise about guaranteed delivery, and it doesn't make any promise about the order in which bytes are delivered. So using the lowest layer, I believe, is giving me the IP protocol socket and not the TCP socket. And an IP socket supports connect, but it doesn't support reliable data connection, which is needed by async read until. I didn't fully research the technical specifics of why I needed to use next layer here and why lowest layer didn't work, but I suspect that's the reason why you need to use next layer here and not lowest layer. And it's just kind of some deep lore about network protocols if you understand like how the layers of protocols are built up in all the internet specifications. But just wanted to point that out in case you were wondering, why did I call the one function here, whereas I called the other function in the other place. So having we're doing the connect, and then we're going into handle connect. Handle connect is going to receive the line that is the greeting. When we get the greeting back from the server, we're going to go into this handle greeting. It does the normal error code style. This error code is not a protocol error. This error code here is relating to like system errors, like, did you, the connection was dropped for some reason, or somebody pulled the network cable out, so you got some kind of operating system error. However, in the chatter that comes back between the client and server for NNTP and many other of these network protocols, HTTP for instance, there's a 3-digit status code that comes back as the first response to any command. And that 3-digit status is the status from the server talking in terms of the protocol. So it's the NNTP status code. And what I've just done is written a hacky little function here that we got our line of data out of the StreamBuff that ASIO stuffed it into. And then I just build an integer from the first 3 characters, and I store that into a member variable cast to the this enum that I'm using to represent the named status codes that are defined in the NNTP specification. So after I've just dumped that line of text out to the conversation window for this connection, it's parsed out the NNTP status code from the response. I'm checking that the response that came back was indicating a successful greeting from the server. There's 2 successful greetings. One says you're allowed to post, one says you're not allowed to post. There's 2 unsuccessful greetings. One says the service is temporarily unavailable, and the other says that the service is permanently unavailable. And after both of those responses, it's going to close the network socket anyway, so there's no point in trying to send further commands. But if we got a successful protocol response from the server, then we can send our capabilities command. This is the text of the command to send. We'll see my little send command function will add the carriage return line feed at the end. And this is the status I'm expecting to see in response. And this little boolean here at the end is whether or not the command returns an associated data block immediately following the response from the status response from the server. So capabilities is a command that you give to the server, and the server responds with a data block that lists 1 capability per line, and each capability is listed with with a name, and there may be optionally additional words after that, separated from the capability name by white space. Each little keyword is also separated by a white space. It says what variants of the capability are supported by the server. So we're going to send this command, and that works. I'm going to stash off the command with the carriage return line feed. Remember some stuff about what I'm expecting to have happen when this command responds. And I'm going to clear my little data block array. This is just a vector of strings. And then I'm going to send a line to the server. And the I call it send line, but really it's just going to send this command string here. I just didn't want to do overloads of send command. I wanted to receive line and send line. So, and then the signature of the callback is an error code and the number of bytes that were written. And I'm kind of just always ignoring the number of bytes that were written. Oh, this is left over from an earlier iteration, this extra false argument. You can see down here that it's not being used. We could take that out. We could say change signature here. We'll just fix this real quick. We'll drop this because it's not used. And poof, now it's gone. So the little false guy over there disappeared, and the unused argument disappeared from our argument list. Because I'm storing that, whether we need to do that in this member variable here. So it's just an earlier iteration of the code. Again, send line, it's going to do it this way. If we're using TLS, it's going to do it this way. If we are not using TLS yet. Now, one difference here is I'm constructing an ASIO buffer from my std string m_command member variable. So ASIO doesn't rely on things like, null terminating byte when sending blobs of data across a socket, because you wouldn't want to rely on null terminated blocks, because how would you transmit a block with a null in the middle? So it always works off of basically what's like a string view, which is a pointer and a length. And when writing data over a socket, the data that is sent is considered const. So it is a non-mutable buffer, a so-called const buffer. And you'll see the const buffer concept in the ASIO documentation. So when you write data, it's reading from the buffer that you supply, but it is not writing to that buffer. It's writing to the other end of the socket. So when you write data, you supply a const buffer. When you read data, you supply a mutable buffer. ASIO buffer is just a function, a convenience function really, that takes a std string and constructs a buffer using the string's data pointer and the string's length. Now, you could also, you don't have to use std string. You can supply the data pointer and the length yourself. And why would you want to do that? Well, you might be building a complex request in a blob of bytes that you've managed in your application, like say cap and proto encoding of a command request. If you're unfamiliar with cap and proto, it's a serialization scheme. We've got a video on our YouTube channel that covers that. You can find that. And a cap and proto encoding is arbitrary byte stream, but it is definitely a pointer to a blob of bytes and a size. And so you could communicate cap and proto messages over Boost.Asio sockets using cap and proto to build the const buffer that you're going to write. Now there's one wrinkle. Just like std string view, a buffer does not own the data that it is referencing. So the buffer is a cheap value type. It's just like a string view. It's basically a pointer and a size. You can copy it around. It's quick. And it does not own the underlying data. So that's why it was important for me to store the data I was going to write into a member variable. And the member variable is on a class that is unique for each NNTP conversation that I'm having. So, and we'll talk about pipelining of commands in a little bit, but I'm not doing pipelining. I am just doing a single individual command. And so it's important that the lifetime of the underlying data in the buffer live until this asynchronous operation completes. That's the important part. So if I did something like, dynamically created a std string temporary that added the carriage return line feed inside this function called sendLine, that wouldn't be good enough, because the temporary, so if I had done something like, if I had done something like that, that's bad. This is creating a std string temporary whose lifetime is only as long as this function call. This function call returns immediately before the asynchronous operation has even started. So when the asynchronous operation goes to try and copy this data out onto the socket, which may take multiple I/O calls in the underlying system API to write data onto a socket, because remember, just because we have a lot of data to send doesn't mean it can all be sent in one go. It may have to be fragmented into a bunch of underlying packets. TCP and IP both have a fragmentation algorithm that they specify that says how large blocks of data get broken up into smaller packets and transmitted, possibly retransmitted, and so on. This temporary won't live that long, so that's bad. So it's important to remember with all these operations that initiate asynchronous calls, all these function calls that initiate asynchronous operations, the underlying data has to have a lifetime that lasts from the time you make the call until the time the handler is invoked to handle the response. So just something to remember here. That's why I store the stuff in a member variable, and that's why I have an instance of this class, and therefore an instance of this member variable per connection. I'm not using a single instance of this class to support multiple servers. I've got multiple instances of this class, one per server. Each one has its own mcommand member variable inside there, so that it's guaranteeing the lifetime of the data that I'm sending as commands. Okay, so we did the connect, we got the greeting, we sent the capability command, and send command gets a callback when the command has been written. And then the first thing we need to do then is to read the response from the server that tells us the status of that command. We get the status line back from the server. We check that the status that the server gave us, that 3-digit code, matches the status that we expected for this command, indicating at the server protocol level that this command succeeded. If that didn't happen, we're just going to return. Otherwise, if the command indicated that it has an associated data block, we need to start reading the data block. Otherwise, if this command didn't send a data block, we're just going to process whatever success result was necessary for the protocol of the command. Question in the chat says, I guess it's okay to have the temporary ASIO buffer. It's only purpose to validate the input with the compiler. So the ASIO buffer, you can think of it like stood string view. It's a data pointer and a length. That's just a simple value type that can be copied around. It's copied into essentially the work item that's put on the asynchronous work queue inside the ASIO IO context. But because it's just a pointer and a length, the pointer is the thing that has to have its lifetime extended until the callback for the asynchronous operation is invoked, if that makes sense. If you think about it, when you use stood string view versus stood string, it's fine to pass all these string views around as deep, as many nested call chains as you want, and store them in member variables and keep using them, as long as the string to which they refer is still live. I hope that makes sense. It's the difference of the lifetime of the data versus the lifetime of the pointer to the data. Obviously, the lifetime of the data has to exceed the lifetime of any pointer to the data. Otherwise, you end up with pointers to invalid junk in memory, right? So, you're welcome. So if we get a data block back, we have to read the lines of the data block. And in the NNTP protocol, data block lines will never be a single period by themselves, because that is used as a terminating line to terminate the data block. So basically, if the data block follows the response of the command, we read a line, as we do here. So we're going to receive a line from the server and then call handle data block line. When we get that line, if it's not a period, to dump out the chatter, and then we're going to store that line in our little vector of strings, and we need to get the next line from the data block. So it's just gonna this handler is just gonna queue another work item to get itself invoked again after we get another line from the server. Once we get the dot, then that was the last line of the data block. And yeah, I just got something hacky here to say if the command was capabilities, and we haven't yet switched to secure communication, we're going to look through the data block to see if it contains the start TLS capability. If it supports TLS, then we're going to send the command start TLS, and we're going to begin this handshaking to bootstrap the secure communication. Otherwise, we're going to send a quit command. I'll show you why that is in a second. So if we go into let's see here, start TLS. If we look for, okay, so when the command succeeds, we called this little, if it had a data block, we're going to go do data block stuff. If it didn't have a data block, we're going to process the success result of the command. It turns the start TLS command does not transmit a data block. So if the command was start TLS, we're going to do this async handshake. And this first argument here, what is this type? I think it's an enum. Yeah. So we are saying we're initiating the asynchronous TLS handshake, and I'm the client. If we go over here, this little enum is like, it's different whether the handshake is not symmetric, right? One side says I'm the client, the other side says I'm the server. If it was, we were using the specific socket for secure communications when connecting to the server, the very first thing the server would do on the connect would be to initiate the handshake from the server side. So we're going to initiate the handshake from the client side. We're doing it in the middle here. And so we're sending the command. We've sent the command in clear text, start TLS. That command came back with a successful NNTP status code that told us, go ahead and bootstrap the TLS communication. Now we're doing that in response to the server told us it was now time to bootstrap that. And as a result of that, when that handshake has completed, it will invoke our handler, and our handler does the normal error checking stuff. And now we just like, okay, now the conversation is using TLS. That all worked. And we're going to send another capabilities command. Only this time, now we've got TLS turned on. So when we get into send command, which will invoke send line, and we're going into this branch where we're doing an async write using the SSL stream instead of the underlying plain text socket. So we'll run this again. I edited that function signature, so it's going to compile something. This warning is just because PD cursors define something that's also defined in a Windows header. So now when we see this stuff spewing out, and I've added delays in here so you can read it, otherwise it would be going by faster. We can see, this begin TLS negotiation. We do the negotiation, it switches to secure sockets, and then all these messages are dumping out with S indicating this is the conversation that happened over the secure socket. We issue the second capabilities command, which comes back with a data block. And if you were particularly observant, you might have noticed that when the data block came back the second time, the start TLS capability was not listed per the specification for NNTP. Once you've switched with start TLS to secure communication, the server must not respond with start TLS in the capabilities after you've switched to secure communication. And then we've issued a quit command, and the server responded with a 205 status and little bye message. And I can just press a key, and then we will exit. So that's all fine if you're like need to do like one and done style, conversation with one of these, long-lived chatty style protocols. But what if you need to keep the connection open while the user types more commands? If I were really implementing a usenet newsreader, I'd be displaying articles to the user. They'd be sitting there reading them. And while they're reading them, there's no network communication going on, and there's no network communication pending. So the I/O context associated with ASIO has no work to do, and it's going to exit out early from the I/O context run. So over in Boost.Asio, in their documentation, in the reference, there's I'm drawing a blank on the name of it now. But basically, they have an example that shows how to do this as well. Basically, what you do is you queue a work item onto the I/O context that will essentially never complete until you explicitly abort it. And that keeps the I/O context alive so that you can receive interactive commands from the user and then generate new asynchronous I/O onto your socket. So let's see if I can find it. Is it called cancel? Sorry, I didn't get that far in my little NNTP example, so I don't remember the exact name of this class. But basically, it's a function that you call and you supply the I/O context to it, and it basically, as I said, it enqueues a work item. You have an instance of this blocker object. I can't remember the name of the exact type, but it's described here in the Boost.Asio documentation. And you hold on to that instance, and then when you're ready to exit and clear the I/O queue, you can basically cancel that object, and then it will cancel itself out of the asynchronous work queue, and then the asynchronous work queue will exit. But this gives you a working example. The curses calls should work on Unix if you want to try and build this code, but I didn't build up the build infrastructure to have it work on Unix. But it might work just out of the box okay if you just compile it. It won't look for the PD curses package on Unix that's marked as Windows only dependency and VC package, so it won't barf out on that. But I haven't tried this on Unix. But it's just standard straightforward curses junk, nothing fancy. It should work fine. But the important part here was seeing how you can take a plain text socket and bootstrap it to using TLS in the middle, of which I couldn't find. It's not that it's particularly hard, but it just requires a little bit of orchestration here. Now, a fully featured implementation of NNTP would implement more commands, and as you might guess, this somewhat crude mechanism that I've got going doesn't scale necessarily to the full repertoire of commands. It's kind of, manually onesie twosie. I'm checking, comparing against command strings and stuff like that. And as these protocols get more complicated, you probably want to separate out a protocol processor that does not interact directly with ASIO, but only deals with the lines of text coming in to the client from the server and lines of text being sent to the server from the client. That's something you can easily unit test, and the logic is straightforward. It can be difficult to test these things when it's a big chain of asynchronous operations. How do you mock that out in a unit test? And the answer is always, when something is hard to test in one place, move it to another place where it's easier to test. And what you see going on in my code here is we've got protocol logic mixed in with asynchronous I/O logic. And that means I'm violating a single responsibility principle. This class is kind of doing two things. It's doing asynchronous I/O and it's doing NNTP protocol logic. So the answer is, as this gets more complicated, move the NNTP protocol logic out into another class that just does that and doesn't do any asynchronous I/O, and then connect it up to the asynchronous I/O machinery, and in such a way that when you look at the asynchronous operations, it's pure delegation, and you can say, okay, it's correct by inspection. I don't have to worry about unit testing the asynchronous mechanism. In addition to that, as the NNTP, it doesn't really require this. It's not that complicated in terms of the protocol itself. In terms of needing like a custom parser, right? I can just deal with std string and a little bit of, searching around for white space. But the payload, the articles themselves, the interesting bit of NNTP, the interesting bit is not these little capability commands and all this other junk. The interesting bit of NNTP is the articles themselves. Well, the articles themselves follow the structure of email messages, which is, an elaborate specification with a grammar that specifies the appropriate, content of email headers versus the body and the interpretation of all the headers and what do they mean and when is, white space allowed, where is white space allowed, how are long logical lines folded into shorter physical lines, and so on. Tons of details in parsing the messages themselves. And there you would want to use a parser library. Boost Spirit is one, and pick one. Yak and Flex, Bison and or Bison and Flex, Yak and Lex, if you like those sorts of parsers. Roll your own recursive descent parser, but for complicated payloads like the messages themselves, a parser is probably a good idea. And now that's yet another responsibility that you probably want to break out into a separate class instead of having it all mixed in with your network protocol logic and your asynchronous I/O logic. Additionally, you may have noticed in the way that I daisy-chained these asynchronous callbacks, it's essentially a state machine. We proceed from one state to the next as each asynchronous operation completes. There's a state machine mechanism in Boost that may be useful in modeling the sequence of states that are implied by the conversation associated with a network protocol. Most people doing these kind of low-level internet protocols, they're familiar with. Most people get interested in this topic by looking at HTTP. HTTP is an extremely simple protocol. You send a command, you get back the answer, and then in HTTP 1, it drops the connection. It doesn't even keep the connection alive for you to issue another request. Later, HTTP gets slightly more complicated, but it's really, in essence, it's like you send a request, and then you get back the payload that is the response. So you typically, like a state machine really isn't necessary, but in a more of kind of sticky protocol like FTP or SMTP or NNTP, a state machine might be warranted. If you're doing your own custom protocol, you might have the protocol might be very context sensitive, meaning the current state of the connection is dependent on the sequence of commands you'd issued earlier. Well, that's state machine, right? So looking at a state machine to represent the protocol states might be advisable. There is a capability in NNTP that we haven't discussed, which is command pipelining. The NNTP specification says which commands can be pipelined and which ones must not be pipelined. What does it mean for a command to be pipelined? What it means is that you can write the command to the server, and before you receive the response for that command from the server, if that command allows pipelining, you can write another command. So I could have several commands that I've sent to the server before I get the response from the first command that I issued. This allows for more efficient communication between the client and the server when there's basically a bunch of data that the client needs from the server. It sends a bunch of data request commands that can all be pipelined, and then it can wait for the results to come back from the server for each of those commands in sequence. Now the results come back in the same order as the commands were transmitted, so you don't get the result of the commands out of order. But there's no, other than the status response that begins the response of each command, there's no indication which command is being responded to in the stream. So if in this code I'm only supporting a single command at a time, if I wanted to support pipelining of commands, I would have to save off some kind of vector of this little information that's associated with each command, and I'd have to keep that information alive as long as the command was in transit until its associated answer came back. It's not particularly hard to do. I thought about trying to get that implemented in time for this presentation, but we've already been talking for like an hour and a half, so it was plenty to go over here. But I think the most interesting part of this example was showing you how to bootstrap the TLS in the middle. You can kind of get a feel for there's starting to be the stink of callback hell in this code, as it got all these daisy-chained callbacks. You can kind of get a sense for it's getting a little bit ugly, that I've got the protocol logic mixed in with my asynchronous I/O, and it might be time to separate those apart. If you look at this code on the repository, I was actually trying to do that with a client and processor class over in this NNTP target, and I had some unit tests that I wrote for it, and the tests are passing, but it was just more than I wanted to chew for this presentation, so I left things kind of mingled together, and the important part I wanted to show was how to do the open SSL bootstrapping. So that's, phew, boy, that was a lot. I hope it wasn't too much for you to swallow. Next month, we'll look at a Boost library for doing HTTP over ASIO. Now that we've seen how to do low-level protocol details and seen what a pain they are to do all of it ourselves, doable but not happy, not fun. We'll look at a library that lets us do HTTP requests and WebSocket requests over ASIO to relieve us of having to negotiate the details of the HTTP and WebSocket protocol specifications. If you guys got any questions, feel free. Otherwise, we will wrap up either in the chat or by audio. Another great explanation and expiration of a new library. Richard, thank you so much. You're welcome. And Ryan also says thanks. You're welcome. Okay, so if there's no questions, we will wrap it up there. And thanks for being here.